All right, welcome back, geometers. This is our first true lesson of the day. We're going to set this up, and then we're going to look at like that explorer start of the lesson idea. In geometry chapter 1, we will begin our study of geometry with foundations of geometry. So we're going to look at the foundational parts. And for me personally, I think that this class will get more fun when we get into the more challenging stuff. But maybe to put your minds at ease a little bit, I don't think there's a ton in geometry that's super challenging, as we talked about yesterday. So we'll just call this foundational skills. Now, part of these skills are going to, what did I say before, Lily? Because I must have said something different than I wrote. Did I say tools before? What are you erasing?
I just started writing before I started listening.
Oh, you're good. Okay. All right. So within these foundational skills, we're going to talk about and define, and it's not the most fun thing to do in a math class ever is just talk about definitions, but it doesn't make sense to talk about stuff if we don't agree what it is that we're talking about. And I made you all move so I could turn that one off and not waste my bulb, so I'll do that. All right. In Chapter 1, Foundational Skills, we will start today with 1.1, and we only have a few things to look at. Chapter 1, Section 1 is how this is denoted here, and we will be looking at how does one go about measuring, talking about, writing, all those good things, but measuring specifically segments, bless you, just kidding, I thought you sneezed, segments and angles. Okay, this is our focus for 1.1. Do you guys know what it means to measure? Okay, do you know what a segment is? Maybe, no, go ahead.
Is it just a straight line?
Ooh,
But like,
it's straight for sure. I wouldn't say it's a line.
Part of a like shape.
Part of a, ooh, I like, let's, not all of it, part of a line. Like a specific section of a line. Because lines go how far, Lily? Yeah, so segments don't. And we'll refine that as well. But every time we start a new section, I want, before we even have like a main topic head or anything like that, we have our explore problem. And we're going to try this today. I'm going to give you 2 minutes, maybe 3. We'll see if we need it. I'm going to put a problem up on the board. You do not have to copy the problem. All I want you to do is answer A, B, however many parts there are, through collaboration with your neighbors. Now, notice I didn't say I don't want you to give me the right answer. That'd be awesome. But I want an answer. Anybody know what is an awful answer to give, even if you don't know how to do it?
I don't know.
I don't know is a terrible answer in math. I don't care, like I do care that you don't know, but I want you to try, because if you get it wrong, that gives me a place to jump in. If I don't know, I could start teaching you what numbers are and how to count on your fingers, which I don't think we necessarily need. Do we? Okay, I don't think so. So, here we go. I'm going to pause the video while you guys do this. I'll always have it here. I'm going to put the video up on the screen. When I start talking again as a whole class, and we start talking as a whole class, if I don't resume the video, please, 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 please indicate. So, here is, not ours, just kidding. It looks like it, but that was algebra. What am I looking for? That guy. Cool. All right. Here is the exploration that I want you guys to do with one another right now. I'll get it centered. All right. So here you go. This, all I need is A and B. You don't have to draw it. You don't have to write down the question. I just need the answers for it, because once you get your text, these will be in there if you need to reference it. Cool. I'll give you 3 minutes. Okay. These problems, they're not meant to be like crazy difficult, I don't think. As we get more used to the textbook, we'll see. Maybe, hopefully, there's some challenging ones. Vincent, you had an option right off the bat when I came over there. You said to find that distance, you would do what?
Just count the thing.
So let's see. Where should I start? From A seems reasonable. Why not B? Okay, that's, yeah, intuition. I'm fine with that. You do not have to draw this. I just want to do exactly what you're telling me. So we could count. Literally, we could count them. I did. I can tell because it says, anyway. So check it out. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. I can count them, right? Okay, that method, it just worked. I know the answer is 8. You probably know the answer is 8. Is there another way, though?
Yes.
Okay, so we can count it. Ray, what's another option?
Using absolute value.
Absolute value. Gosh, what do you mean?
Absolute value is you basically just make your number positive if it's negative, and know how to actually get absolute value, I mean, it's pretty simple. You just make negative things positive and.
So I'm going to make
keep
it,
positive
it's a
things.
weird thing to explain right here
Yeah.
and now. Let's check it out. When we think about absolute value, which is how I would think about this problem, and we'll see why I would think about it that way, how far from 0 is this number? So careful. How would it be negative 3 away?
Oh, wait, never mind.
You're close. How far would you have to walk to get from A to 0 or from 0 to A? 3, right? It just changes to positive. Like, that's the absolute value. How about from 0 to 5? And then you would do what? Add them. Okay, so when we do this, what do we get?
8.
8, all the same. Or, another way of thinking about this question, it's the same mathematically. Do you agree that I'm just looking for how big is the difference between these? So, now we'll tie in that absolute value a little bit more specifically. If I wanted to write an absolute value down, how do I write that? What's the symbol for absolute value?
2 lines.
It's vertical bars. Like, that's it. So if I wanted to, I could just say, hey, what's the distance between 5? And if I'm looking for the difference, what does that indicate? Is a difference a subtraction or an add? Subtraction. So let's try this. One number is 5, and I'm going to subtract and find the difference between that and what? Try again. Negative 3. What happens when we remove a negative? It turns to a positive. That intuition, if you don't have that developed, we're going to lock it in. I'm more than happy to show you like a bunch of examples and ways to think about this and why this happens. Big add might be what somebody calls it. I'd say minus a negative plus a positive is my language. I think Russell used to use leave, change, flip or something. I don't remember the language exactly. Either way, what's 5 plus 3 become? 8. Now there's a benefit of using these absolute values, and we're going to dig into the distance and all that stuff today. Why did I start at 5? Because it feels like the biggest number. What if I didn't want to? Could I start at negative 3? Let's try it. If I had done this the other way, and we'll just dig in. If I had started at negative 3, I'm looking for the difference between negative 3 and what? So it's still minus 5 though, right? Just minus a positive this time. What's negative 3 minus 5? So that'd be a negative 8.
But
It's an absolute value, so what do we do with it?
find its distance, which is just 8.
Yeah, how far from 0 is the number negative 8?
8.
8. Look at that, it turned positive. And we get the same answer. We just saw 2, maybe 3, if you want to like really separate them, different approaches to solving this problem. Which one's the best?
Absolute value.
So you say the first one, Ashley, it's probably simpler to think about, right? I'm going to show you
Well, I mean,
pretty objectively that you're wrong, and not in a bad way, because everybody probably would prefer to count. It seems the easiest. I'm going to make a pretend number line real quick. You don't have to draw this. Number line, I just did those instead of individual ticks. Okay, here's the number negative 1,038,652.1 and 17.372. Are you going to count those ticks? Do you know how long a million seconds is?
and you actually, those ticks could be all the way, not even seconds. They could be.
Yeah.
years.
A million seconds, I think, is like 11 days. Crazy thing, how much time is a billion seconds?
Like 3 years.
31 years. 11 days is a million seconds. You could count to a million. It would take you a lot of time. You probably don't have enough life in you with sleep and eat and all that to count to a billion in your life if you count by one. The tick method probably won't work here. Not feasibly anyway. So what we're looking at today then is how do we make sense of this and how can we apply the same idea in a variety of contexts and start thinking about angles. Cool. So every day we'll start with this Explorer. It may not always go this far in depth, but it'll be up on the board so that as you're doing that, what I would like you to do is have your homework out if I give you homework. Work on the Explorer for 3 to 5 minutes. I'll come around and check to see your homework's done, and then we'll go over the homework and the Explorer and jump in. Cool. All right. So with that, let's actually dig into this. So you guys have a little bit of work on yours. I'm just going to jump in right here. Now, other things that we're doing just as a district. Last year, do you ever remember Miss Hanish walking in and asking you, like during a lesson, like, hey, what are you learning today? How will you know that you know it? Like, how did you answer it, just out of curiosity? Because I don't know how I answer that question. Okay. So if somebody walked in right now and asked, what are we learning? What would you say? Measuring segments and angles. That's reasonable. I'm not really offended, just so you know. What I'm going to start doing, I'm going to move them to back there instead. That's like the 5th time that's happened today. What I'm going to start doing is I'll have these up every day. If you want to see them, you can. My hope is that even if I didn't write these, if you're paying attention, you could tell me what we're doing. But today, my goal for you guys is that by the time you leave here, I want us to know how to use the ruler postulate and the addition postulate and the protractor and angle postulates, which you might have never heard of those. There's probably, I don't know if you've ever seen that word either, but we'll knock them out. That's our focus today. If somebody asked me, how would you know it? Like, how would you show me you know it? I don't know that I would change anything. I would say, oh, I would show you that I can use this stuff. Like, I don't know that language. I wish I had better advice for you. But let's check it out. So, we have one big question. I want to know, how do segments and angles help us to determine measure? That's what we're really looking at. So, to start us off right off the bat, we need a little bit of vocab, and I know it's not fun, but some geometric figures is what we're going to talk about. Now, we know a lot of figures, and you might think of shapes instead, but there's a weird little distinction that we need. Give me a name of a shape. Square, triangle, 4-gon, 5-gon, 6-gon, I don't care how many sides, right? Is a circle a shape?
Yes.
Is a cube a shape?
Yes.
Yeah, it's 3-dimensional, but it has a 2-dimensional shadow if you want it. Here's where it gets weird. Is a line a shape?
No.
It depends on who you ask. Now, it depends on really how you think. You've never seen a real line. This, even, that's going to be way too big. If I were to just draw a straight thing, this isn't really a line. And there's a reason that it's not really a line, but we're going to knock that out. So, there are 3 big ones that we're going to start with. Anytime that I do vocab, how do I write my vocab? How do I indicate it's vocab?
Capital.
All capital. So, right off the bat, within geometric figures, we have this super weird idea, because we're about to define these as best we can, but they're referred to as the undefined terms. So within our geometric figures, our first focus is on 3 separate undefined terms. Now, I didn't call these shapes very specifically because they're not going to classify in my idea, but a figure would indicate shape, line, whatever the case is. So here's my challenge for you. Just yes or no. Do you know what a point is?
Yep.
Okay, so before you write it, you think so? Like, everybody knows what a point is, I assume? All right, here's my challenge. Prove it. Don't write anything. I want you to talk it out. I'm going to give you 3 words right now. Start thinking about each of them. I would just only discuss. We'll come up with an agreed upon definition. But a point, everybody should know what a point is. Okay. Next, we'll have a line. Does everybody know what a line is?
Yes.
Maybe. Okay, and there's one more. A plane. Not like, but like the coordinate plane is an example of this. Okay. The third one, maybe yes, maybe no. I don't know where you're individually at. Here's my challenge. I'm going to give you 60 seconds. Everybody knows. Do you know what a plane is?
Flies me places.
Like, so yes, airplane would do that. Like the Cartesian plane, the coordinate plane, when we think about that. Okay, so here's my challenge for you. Don't write these down, unless you're going to forget it. Like, write these 3, but don't write down the definitions. You guys are going to get 60 seconds right now. I want, in your own words, to tell me what is a point, what is a line, what is a plane. Don't read your book while you're doing this. Okay. If you already have, cool. Like, I want you to use your book if you want to. I'm good with that. 60 seconds. I'll find my timer. Come up with a definition with your neighbors. We could all identify at least points and lines if I drew some on the board, right? But I would never really be able to draw a point on the board or a line on the board. And there's a very particular reason for that. Points are used to represent something in math. And we'll look at the math point of view. If I were to place a Cartesian plane up here, and let's get a Cartesian plane up here real quick. If I have a lovely Cartesian plane, I can put a point in, right? Like, I can ask it to plot a point. Give me a point.
3, 5.
Okay, so I'm going to ask you guys to close your eyes for like 5 seconds. 3, 5 is what I heard. Okay, I'm going to have you open eyes in 3, 2, 1. Did I plot the point 3, 5?
No.
Okay, I'm going to hover it. We're going to check it.
Yes.
Gotcha. There's an issue. This is not the 0.35. It's actually not even that point. It just didn't understand how to round it. This is the point that I asked it to do. Can you tell? No. Now, if I zoom in really close, you might be able to tell. If I zoom out further and further, it's a larger area where you're not able to tell, right? Okay, there's something weird about points. We draw them all the time, is what, like, you've learned to plot points. The real language isn't that, though. What you've really learned to do in your algebra and your math is you've learned to plot the representation of a point. You've never actually done the point. And because a specific location in space, you wouldn't be able to see a single individual location in space on a page anywhere. We draw big dots, right, to represent it. But this dot definitely covers a bunch of stuff that's really close to it that's not just that single location. So I need to find a good height level because this one's not quite working. But let's check it out. By definition, we're going to say the following. A point. Couple things. First of all, a single location in space. Now, because it is only a single location, and the physical world is harder to think about this, a single location in space. It means we couldn't ever actually draw it because it would cover multiple locations. We represent points with those dots on the board, but we never see the true point itself. Okay, when we're looking at these, a single location in space, the big takeaway from this is that every point that you will ever work with in reality has no shape. We draw little circles, but in reality they don't because it's just a location. No shape or size. There's no width to a point because it would cover multiple locations. It can't do that. So a single location in space is the best that we can do, and then there's no shape and no size to them. Don't let that confuse you. Do we have a shape and a size when we draw a point, quote unquote, on our page?
Yes.
But it's not a real point on your page, it's just a representation. Now, the last little thing that we're going to deal with is when we're talking geometry, their notation here is more important than it's been in like any other math class that you've taken. We have to be careful and use it to agree that we're talking about the same thing. To denote these or to write these down, we use, and I don't know how I want to, we'll just do it here, asterisk, we use a single capital letter. A single capital letter. Okay. Always, 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 which is why you will learn the NATO phonetic alphabet. Now, we'll do an example where we'll have a plane, a point, and a line, and we'll practice with these. Single capital letters. Default, for me, I usually start at A, but it's completely arbitrary. It could be A, B, C, don't care. Okay. All right. What'd you guys come up with for a line?
A line.
So a line. Go on.
A line is a line.
What makes a line? Like if I wanted you to draw a line, like a very specific line, what would I have to give you?
Points.
How many? At least 2. So I'll do that up here on the whiteboard. Like that's fine. It won't be perfectly straight. We'll just pretend it is. Okay. This is a straight line, roughly. Like we'll even say it's straight. What's it made of?
2 or more points.
Ooh, we're gonna focus in on that. If I wanted you to draw this, I might give you this point and this point, right? Seem reasonable?
Yep.
Are there more points on this line?
Yes.
How many more points are there?
Infinitely.
So to draw a line, how many points do you think you need? You need 2 to just have an idea of it, but how many points are actually on here?
Infinite.
Infinitely many. So check it out. We'll say that a line, by definition, is there a symbol for infinite?
Yes.
Do you guys know it?
Sideways. A.
Good. It's called a lemnis skate. But yes, this is a sign. Infinite points. Is this a line? I'm going to draw something on the board. Is this a line? I'll even do this to make it a little bit more confusing. I'm going to make a claim. I'll even switch this. That's not a line. Why not?
Because it curves.
Ooh, it's a curve. It's not a line. It's a curve. They're different. Lines do what?
Go straight.
Yeah, in a straight path. Now, we can use our lovely powers of logic to make some sense out of this. Points, how big are they in reality?
Like nothing.
Nothing. Literally nothing. There's no shape, no size. It's just a location. Okay. So you have something infinitely small that's no size, no shape, and you put a bunch of those together. If I put something with no shape or size with another thing with no shape or size and combine them, which is a weird idea. Do they have shape or size yet? If a point doesn't have any shape or size and a line is just infinitely many points, does a line really have any shape or size? No. So just because it's same thing, because it's made of these, no real shape or size. In reality, there's no thickness to these. If I tried to draw a line with no thickness, you ready? I'm going to do it. It's beautiful, right? Like you just literally can't touch the page. So we'll just go ahead and say no thickness. Okay, but extends forever. Okay. When we write lines, we will use one of two conventions. There's two options to choose from. Both of them are equally good. I know which one I prefer, but you guys, I'll let you choose as we're doing it, and I'll try to stick with whatever you want. To write these, we use a single capital letter for a point, right? Okay, so let's underneath, we're going to draw a line, and I'll draw my best representation of a line, and we'll see how to name this. So I want 2 points is what I need to name it. Any 2 points to put on this line. 1 and 2 are weird choices. What do we use to represent points?
0.
Nope. What do we use to represent points? Capital letters. We need a letter. A and B? I'm good with that. I'm going to say here's point A, and over here is point B. Are there more points that I just don't name?
Yes.
How many more points that I just didn't name? Infinitely many of them. Okay. To name this, we have a line. It goes on forever in a straight path. 2 ways. Option 1. Let's say to name, and I should have made this more consistent, so I'm sorry about that. We have 2 options. The first one, I don't care which path, which point we start at. Where would you start? A, B? A to B, right? Okay, so if I write AB like this, and this is where like ears and eyes open because this you're going to see this and I will destroy you for this, just so you know. I don't have it yet. If I write AB with this, it means something different than what I'm after right now. I want to name this thing as a line. A line goes how far in each direction? So we need to make sure that this is here. Okay, this is a pretty common way to name a line. If I do on mine, you don't have to on yours, there are more points on this that I just didn't name. Let's say I want to get real crazy. Don't add it to yours unless you want to. Could I add point Z is on here somewhere? Is that still line AB?
Yes.
If you run a single or infinite collection through A and B, will Z be included?
Yes.
Give me another name of this line.
AZB.
AZ.
Oh.
2 points is all it takes. Give me another one.
ZB.
ZB. Another one?
There's none.
BZ. BA. Like the order doesn't matter for a line. As long as you include any 2 points that are actually on that line, all infinitely many of them are included. Okay, there's one way to do it. 2 points. Never use 3. Okay, alternatively, what you will see is oftentimes mathematicians are lazy. They don't like to write much. I get it. You will regularly see lowercase italic letters next to these things. So if I write, for example, a lowercase italic A, I could call this line AB or BA or AZ, whatever those combinations are. Or what else do you think I can call it? A. Line A. We'll say 2 points or line A in this case, or M or L or whatever letter you wind up using or seeing. We can just simply call it line A. Okay. Again, I'm going to be crazy about this. If you give me line A and you use a capital A, I won't give you credit for it. Like, we have to be so specific with these things. Okay, couple more, and today's pretty much just a vocab day. If we need a break, I'm happy to do so as soon as we finish playing here real quick. Okay, everybody's seen the Cartesian plane, I think. Okay, it has 4 quadrants, A, or 1, 2, 3, 4, x-axis, y-axis, origin, Some of those things probably sound familiar, some of them might not. But we get to a plane here. Now, when you think of drawing a plane, what sort of surface are you working on? Flat. We don't use planes on curved surfaces, right? It doesn't make sense to try to do it. So a plane, really easy to define. We're going to say that a plane is just that collection of infinitely many points again, but they don't have to be in a straight line. We'll say infinitely many points on a flat surface. Extending forever. Okay. We have to be on a flat surface with it. Now, where it can get weird to think about is if I look up here and I put my hand on the whiteboard. Is the whiteboard a flat surface for, I know it's not perfect, but for all intents and purposes, it is flat, right? Yes. So there's a plane right here. Now, if I'm using the whiteboard as my plane, I'm only going to draw on the whiteboard. But is it possible that a point exists up there on the wall that I'm just not going to draw because it goes forever? Yes. Like, I could extend forever. Could I let this book serve as a different plane even though it's at this wonky angle? There's a flat surface that I can imagine extends out this way, this way, this way, and this way, and stays flat, and it goes forever and ever. To name a plane, how many points do you think we need? 1 point names a point. How many for a line? 2. Now, logically, and just by, patterns, what do you think the third one will be? 2 points will name a plane? Why? Why not 2? So check it out. I will show you exactly why not 2. Can we agree that this is a flat surface? Yeah. Okay, I'm going to use 2 points on either side. I'm just going to put my points here. If I said, hey, this is going to define a plane, it means that no matter where this piece of wood is, we should be on the same flat surface. But I can do that. This thing pivots. Is this plane the same right now, this flat surface that's like parallel to the ground? It's a flat surface. Is that the same plane as this? No. No, so 2 points doesn't do it. Even if we try to put them here, I can still do this, and that plane is differently aligned every time. Do I need a third point to anchor this up? So how many points do you think we're going to use to name these bad boys? 3 of them, absolutely. So how we name them is important, and we'll look at that. But we're going to say infinitely many points on a flat surface, and then when I draw my planes, I always draw parallelograms because I feel like it gives me a little bit of depth to it. If you just want to draw a rectangle or square, I'm good with it. I'm looking at a 3-dimensional figure. It's like this is what you're viewing right now. From your perspective where you can see it tilts and stuff. Cool. So for this plane, we name with 3 points. So let's put 3 points on this bad boy, and we're going to pick different ones so we don't get them confused. Let's see. A is for Ashley. L is for Lily. And Carson, it's with a K, right? Yeah. Okay. Now, we're going to just introduce another word. Your book doesn't use it in the definition, but I'm going to use it to make sense of. Can you make a single line through all 3 of those points? No. Okay, so that means that they are what's called non-collinear. They do not fit on the same line. Co meaning together, linear meaning line. They are not on the same line. We have 3 non-collinear points. So 2 ways that we can name these. You can do this, and I'm just going to put this here, same convention. 3 points, and they have to be non-collinear. They cannot be on a straight line. So, what are the 3 non-collinear points on this plane right now? Plane ALK. Order doesn't matter. If I add a new point up here, and we'll call it M. I'm not certain because I didn't do it perfectly, but do you think AMK would be a good name for that plane now? Can you see any reason why it might not be great? So
it looks too much like a line.
It looks like a line, right? And maybe it is, and I'm just a bad artist. If I do this, we run into that situation where everything could change orientation. We need 3 non-collinear points. And you're going to see my spelling issues. I think there's 2 L's. But it looks wrong. I don't know. Non-collinear. I think it's double L, but if I'm wrong, I'm sorry. Okay, an alternative though, because again, mathematicians don't like to have to write the word plane every time. We use a single capital letter for a point. For a line, we use 2 points, so regular capital letters with this mark above it. It has to have the mark if you're talking about a line. For a plane, oftentimes we can use this and write this out, or we can have a uppercase or capital italic letter. So for example, I like to make mine super obnoxious. So here's a B. Is there a point clearly on that plane that we associate with that letter B?
Yes.
Where? So there are points on it, but is there, like this A, for example, and I'll point here so it's on the video. This point A, I think, is reasonably associated with this dot. This M is that dot. What dot is B?
All three.
Maybe, like there isn't one, right? This is our indication with their capital non-italic, or capital italic. We can also name this simply plane B, just like we do with our lines. Okay. Now, I would like to take a really quick brain break of some sort. What do we want to do? Really quick, any ideas? I got lots of... Did we deadpan in here yesterday? Was that this class? You have no idea what I'm talking about, do you? All right. So, do you guys know what it means to be deadpan? Straight-faced. Here we go. We're going to introduce 3 more, but I'm going to draw a big picture to help us. And up to you if you want to draw it. I would encourage, at least for this first one, you should. But I'm going to draw a large parallelogram-looking thing here. Doesn't have to be perfect. I will hook you guys up with straight edges in the coming days. And then I'm going to have a fancy A right there. I will have this thing right here. We'll call this X, T, P. All right. As we're looking at this, I'm going to try to go a bit quicker. Maybe we don't have to formally define everything, but the notation is going to be important. I have a few questions for us. And I'll give you a second because I can tell some people are still drawing. This is where we talked about the binders and stuff. Like, if I could print these out, it'd be easier. I don't know the right way to do it. All right, check it out. Somebody tell me a name of a line up here. TP. TP. Vincent, give me another name for a line up here. XT or XP. I'm cool with that. Now, we've seen lines. Is there a section of that line that we could say it starts here and ends here specifically? So let me rephrase that. Could you select only a section of the line?
Yeah.
Could you tell me to start here and end here?
Yeah.
Give me an example of where I might be able to start and end. If I start at X and I end at P and I don't go to infinity, do I still have a line? How far do lines go? So if I don't go to, what is going on here?
What would you call it if it is?
That's a great question. What would I call it if it doesn't go infinitely far? My goodness, it's a segment.
It's like, oh,
So,
we saw that.
a line segment, and I don't need a bullet point, I just want to see the same way. I've been using dashes. Okay, we have line segments, which formally we'll just call a segment. If I only want the part that's going to be red, just this, it doesn't go forever. There's still infinitely many points on it because there's no size, so infinitely many of them fit, but it doesn't go out infinitely far. For a segment, we have just a section of a line. A finite section of a line, if you want that to be more specific. A finite section of a line. Now, when we deal with these finite sections, we want to be able to name them, right? So, looking at this, if we wanted segment XP, is this correct? Is what I've drawn correct before you decide to copy it?
No.
Why?
Because it,
Put the arrows
yeah.
on the end.
So what do I do?
You keep them off.
Yeah.
Bless you. Right now, I know that I have X and P as my ends of it. Does it go on forever anymore? Boom. We have it. This is a segment. Give me another name for the same segment, XP. PX is the only one that works. Another segment up here, XT. Just this is a segment, right? All right. Let's get crazy real quick. I'm going to switch this around just a skosh. I'm going to give you an example of what I would name it, and I want to see what you come up with calling it. Okay. Could I start at X, go through T, and go forever after that? So I'm going to try it, and we'll see what we come up with. So here we go. I'm going to leave it blank here because we're going to put a name of this. But I want to know, what if I did something like this? XT, and I said, hey, it goes on forever, but only that way. Only one direction. Is that a line?
No.
No, it'd have to go forever both directions. Is it a segment?
Yeah.
It goes forever, though, because segments don't. And that's like that line, that bar above it, that tells me it's a segment. This is somewhere between a line and a segment. Does light travel straight paths, typically? We're going to say yes. We'll just, like, I've never seen light bend. I know the universe does it, but we'll just assume it does. Where do we get light naturally outside from? It's the sun, so it's a straight path, right? Where does it start? At the sun, or in space. And if it didn't hit Earth or anything, how far would it keep going? So it would have a specific starting point, and it would go forever, right? It'd be a something of sunshine. Ray? All right, we have rays. We get rays in class, in geometry, from the sun. We define a ray. Okay, this thing, does it have a specific starting point?
Or yes.
This one does. Where does this ray begin?
X.
And it goes through T and on forever. So starts, then it goes forever. And I'm going to say to infinity as my forever because that's shorter to write. Is this the same ray? Sorry, I'll make it more arrowy.
No.
It's the opposite direction. The way that you name them here matters. Lines don't care. Segments don't care as long as it's the endpoints. This one does matter. Okay. They're opposite rays. I'm not going to bother writing that down. If they start at the same spot but go opposite, together they make a line. They're just rays that are opposite. Everybody cool without writing that? Opposite rays, exactly opposite directions. Cool. All right. So I'll even say opposite right here, just so we don't have to have our own section. All right. There's one more thing that I'm going to put up here. I'm going to add one little piece to this picture that I have. I'm going to say from X, I want to have ray XR. So I'm just going to put point R somewhere, and I'll say it goes forever. I'm going to claim that I've just formed something that's going to be a fundamental point of study for us.
Angle.
We have formed an angle. Okay. When we have angles, we will jump in with this tomorrow. We didn't finish this section. Tomorrow I'll have a very specific practicing with all this. We will jump in tomorrow. We will define angles, talk about how to name them, and then we'll get a little bit of practice with this. The first section is essentially getting the hang of this through a couple exercises. Cool. No homework tonight. You guys have a wonderful day. And yeah, I'll try. Cool.
I mean, at least you don't have
Peace
to
out.
limp to school.
Yeah, no, I'm still kind of hurts.